In this video, we will look at advanced smart contract development with Solidity. We will look at better techniques in Solidity for developing robust and efficient smart contracts. We will first look at more advanced features and concepts of the Solidity language building on the foundational language. Then we will understand how to leverage inheritance and interfaces to create modular and extensible smart contract architectures. Then we shall learn about Solidity libraries and how to use safe math to prevent arithmetic errors. Advanced concepts in Solidity that go beyond the basics of smart contract development. Concepts help in keeping the contract more secure, more efficient, and have better maintainability. This advanced Solidity is like mastering the art of constructing complex, secure, and high performance buildings, ensuring they are not only functional but also efficient and secure. Inheritance allows developers to create new contracts based on existing ones, promoting code reuse and modularity. Interfaces define the function declarations without implementing their functionalities. Inheritance and interfaces in Solidity are like blueprints for buildings, allowing architects to reuse designs and ensure different parts of the building adhere to specific standards. In this code example, we have four smart contracts. The first one is the base contract. This contract has base message string variable and a function setBaseMessage to set the base message. Then the derived contract inherits from the base contract and adds a new derived message string variable. It then provides a function setDerivedMessage to set the derived message. The iMessageContract.solve is an interface. It declares two functions, setMessage and getMessage. SetMessage is an external function to set a message, whereas getMessage is an external view function that returns a string. Then the messageContract.solve implements the iMessageContract interface. It contains a private message string variable. It provides the setMessage function to set the message and provides the getMessage function to retrieve the message. Now we will use libraries and the SafeMath library in particular. Libraries are reusable pieces of code that can be linked to contracts at deployment time. SafeMath is a library that helps prevent integer overflow and underflow errors. Libraries are like prefabricated building components that can be used in multiple construction projects to ensure safety and efficiency. In this code, we see functions in the SafeMath library. The add function, which will throw an error if the u in C is lesser than a, or the subtract function, which takes how two uints a and b and returns a minus b only if b is lesser than equal to a. Otherwise, it will throw a subtraction overflow error. This is an example of how to import the SafeMath library and write a contract. We can see the utilization of the add and sub functions in the SafeMath library. So modifiers are used to change the behaviors of functions in a declarative way. Function overloading allows multiple functions with the same name but different parameters. Modifiers are like special instructions that modify how a function behaves, while function overloading is like having multiple variations of the same tool for different purposes. Modifiers enhance security and maintainability by enforcing access control and other preconditions in a reusable manner. Function overloading provides flexibility and improves the readability and usability of the smart contract. Here is the example of a modifier code. The only owner modifier here restricts access to certain functions. It requires the caller of the function to be the owner of the contract. If the requirement is met, the function body is executed. Otherwise, it reverts with the error, not the owner. Here, we see the same add function with different parameters in the function overloading contract. The first add function has only two parameters a and b, whereas the second add function has three parameters a, b, and c. Events in Solidity are used to log info on blockchain. They are a way of contracts to communicate with off-chain applications. The events are like security cameras which store the data for future reference. This contract declares an event message set which logs a single string parameter. Then we declare variables and have the set message function. Now, after updating the message start variable, the function emits the message set event logging the new message. The emit keyword is used to trigger an event. Error handling in Solidity is done by using require, assert, and revert. These functions help catch errors and ensure that the contract behaves as expected. They are basically safety checks to prevent and handle failures. Require is used for validating inputs and conditions. Assert is used to check for internal errors and invariants. Revert explicitly reverses the transaction. In the following code, we can see in the function safe_divide, it requires the condition that the divisor always has to be greater than 0. Then we use the assert keyword to check whether the result multiplied by b is equal to a. Then we return the result. Then the check condition function demonstrates how to handle conditions that might fail. It checks if the condition is false. If it is, then the function reverts with the message condition not met. Now let us optimize gas usage. It is crucial for writing efficient smart contracts. The techniques include minimizing the storage operations, using efficient data structures, and avoiding costly operations. It is like designing an energy efficient building to minimize operational costs. In this contract, the add data function adds a new value to the data array. The built-in push function, which is efficient for appending elements to the array, is used here. The sum data function calculates the sum of all elements in the data array. By storing the array length in a local variable, the function avoids repeatedly accessing the array length during each iteration of the loop. This optimization reduces the gas cost as accessing a local variable is cheaper than accessing the storage. The loop also has been optimized and the loop iterates over the array elements and accumulates the sum. Using a local variable for the loop index and array length helps minimize gas usage. These upgradable smart contracts are mutable and can be easily used to remove any bugs without changing the main functionality. In this proxy contract, we have the state variable implementation address. This variable holds the address of the current implementation contract. Then, the upgrade function allows upgrading to a new implementation contract by changing the implementation address. This makes the proxy pattern flexible and upgradable. The fallback function handles all calls that do not match any function signature in the proxy contract. The fallback function uses inline assembly to perform a delegate call to the implementation contract. Then we shall avoid reentrancy. We shall design our contracts functions to prevent reentrancy attacks. Then we shall use well-audited libraries such as OpenZeppelin's contracts to reduce the risk of introducing vulnerabilities in your own code. We will learn about this in more detail in the next video. We learned how to use advanced Solidity features such as inheritance, interfaces, libraries, and modifiers. We also figured events and logging provide a way to record and communicate contract actions. Error handling, gas optimization, and upgradability are crucial for efficient and maintainable contracts. Also, we need to follow good security considerations for writing robust smart contracts. These are some of the questions you can solve.